So we want to understand quantum numbers. We want to understand quantum numbers. Now, maybe the first thing is we need to understand first an overview before we get to come to the quantum numbers. We said an atom has got the nucleus where protons and neutrons are found. We have got the shell, right, where electrons are found. Now we say the other name for shell is energy level. Now the shells are going to be divided, each shell is going to be divided into what we call subshells. The other word that we use for subshells is sublevel. Now these sublevels have got regions within themselves where the probability of finding an electron is maximum. That's called an orbital. Now basically what you are able to see here, we are going to represent each of these with a quantum number. So a shell has got a quantum number, a subshell also has got a quantum number, and an orbital also has got a quantum number. So we need to understand that. Alright. So the first quantum number that we should be able to know, one is called the principal quantum number. So to simplify things for myself, quantum number I'm going to use Qn. Alright, the principal quantum number. What is a principal quantum number? That is maybe something that we need to get to understand. What is a principal quantum number? So a principal quantum number is simply the representation of the energy level in which an electron is going to be found. Okay, this shows the energy level in which an electron is found. So because of this, in other words, when you're talking of principal quantum number, all we're talking about is the shell number. So the symbol for principal quantum number is small n or n. So we're going to see n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, just like that. So that is what we call principal quantum number. The next quantum number that we have is the angular momentum quantum number. Okay, now what is the angular momentum quantum number? So the angular momentum quantum number contributes to the angular shape and to a less extent energy of a shell, right? So when we are talking about the angular momentum quantum number, now some books are going to write this as the other name as Motho. So we're going to hear that it is as Motho quantum number. So that is angular momentum quantum number. So this one tells us the subshell, okay, the number of subshells present in the many shell and the orbital to which an electron belongs. All right. So angular momentum quantum number tells us the number of subshells, right? The number of subshells which are found in a shell. Okay, so that is the angular momentum quantum number. The symbol for angular momentum quantum number is m. Is actually represented by L. Okay, that is the angular momentum quantum number. Are we good? Are we on the same page?
Yes.
Alright, so the symbol for angular momentum quantum number is L. Like I already said, momentum, if you remember, I said momentum is given by L. So you can think of that angular momentum quantum number. Now, how do we find angular momentum quantum number? Angular momentum quantum number is found by n minus 1. So meaning that for the first shell n is equal to 1, the angular momentum quantum number, now it is not necessarily n is equal to 1, but n is a range. Okay, so you start from 0 to n is equal to 1. So that means the angular momentum quantum number in the first shell is just going to be n minus 1. That is a 0. So you have got 0. For the second energy level, the angular momentum quantum number, the first one should be 0. The next one, okay, the next one, you say n minus 1. That is what? That is a 1. For n is equal to 3, angular momentum quantum number, we've got n is equal, L is equal to 0, L is equal to 1. 3 minus 1, that is a 2. So up to 2. For the fourth energy level, angular momentum quantum number, we've got 0, 1, 2, and 3. In other words, they're going to be 4, 1, 2, 3, and 4. Okay, but to give their exact values, you subtract, like from a 4, subtract a 1, and then we're going to start from 0. So this is how you get to give the angular momentum quantum number. Alright, now from the angular momentum quantum number, we have got another quantum number. Don't worry, you understand more. I'm going to come back to explain more. The other quantum number is called the magnetic quantum number. Okay, magnetic quantum number, which is represented by m with a sub l. Now, what is a magnetic quantum number? The magnetic quantum number involves the level of degeneracy of the orbital, right? The level of it is degenerate. Or angular momentum quantum number represents the orbitals, all right? Describes the orbital. So it's going to describe the orbital's orientation. Orbital's orientation, like how is this orbital in this subshell, which is in an energy level. The subshell, let me just say something again. Angular momentum quantum number, we say that's a subshell, right? This one also describes the shape of the orbital, okay? The shape of the orbital. And then the magnetic quantum number describes the orbital's orientation in space. How is the orientation of an orbital in space? Now, the last quantum number, I'm going to describe them for a second time, is the electron spin. Electron spin quantum number. Now, for this one, it just describes the spin. The spin is just a direction. So, the direction of an electron. Okay, the symbol, this one is m with a small s. So that is the electron spin direction of an electron in an orbital. Now, an electron can only have two directions. So it can either point up or point down. So that is the direction of an orbital. I mean an electron in an orbital. So if the electron is pointing up, it's going to have a positive half spin. If it is pointing down, it is going to have a negative half spin. Alright, so before we describe more, is this okay? Are we good? Okay, are we moving at the same pace? Do we have anyone who is left out? Alright, now remember we have got angular momentum quantum number, which does what? Describes the first we have got the principal quantum number, which describes the orbital size and energy. Alright, the angular momentum quantum number is going to describe the energy and the size of the orbital. That is the principal quantum number. Why does it describe the size? And remember, we said each energy level has got its own energy, right? Okay, that's why you even call them energy levels. So this is n is equal to 1. It is a small energy level. N is equal to 2. So depending with the energy level, also with energy and also the size. So the principal quantum number just shows the energy level and it describes the energy and size of an energy level. All right. And then we have got the angular momentum quantum number, which you can think of as a subshell, which describes the orbital's shape. So what is the shape of the orbital? Okay, the shape of the orbital. And then we have got the magnetic quantum number, which describes the orbital's orientation, right? The orientation in space of the orbital, that is described by the magnetic quantum number. All right, and then we've got the electron spin, which just describes the direction of an electron or the spin of an electron. Okay, good. Now, let me do this. So we've talked of the angular momentum quantum number. We know its symbol and the rest. So let's start with, if we have got an angular momentum quantum number of 1, what will be the what is going to be the if we have got a principal quantum number of 1, n is equal to 1, what will be the angular momentum quantum number? Who can answer us? If we have got a principal quantum number of 1, what will be the angular momentum quantum number? Yes?
It will be 0.
It is going to be 0. So angular momentum quantum number represented by L is given by from 0 dash 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 to n minus 1. But here already n is 1, so it will be 1 minus 1. So that means that this part is not going to be there. That means that L is going to be 0. Now we found the angular momentum quantum number. We have got the principal quantum number. We also need to determine the magnetic quantum number, ML. Now you need to know that ML, which is the magnetic quantum number, is just a number between negative L and positive L. Okay, negative L and positive L. So that means if L is 0, meaning that ML, which is the angular momentum quantum number, will also be 0, right? So I'm not putting any electron here, so I can't determine the electron spin, which is ms. That is the fourth uh, quantum number. We have 4 quantum numbers. So the electron spin, I can't describe it, so I'll just put ms there because I don't know the electron. I've not seen any electron inside. So if I've got the second energy level, n is equal to 2, the angular momentum quantum number here, we are going to have angular momentum quantum number 0 first, and 2 minus 1, that is going to give us a 1. That means we're also going to have 1. So we're going to have 2 angular momentum quantum numbers. So for this angular momentum quantum number here, all right, for that angular momentum quantum number which is there, the magnetic quantum number, ML, is going to be between 0 and 0. Now we don't have a number between 0 and 0, right? So it will just be 0. But for this angular momentum quantum number, when L is equal to 1, remember ML is a number that is between positive L and negative L, meaning that you get 1, a positive and the negative, and all the numbers between, meaning that ML is going to be negative 1, 0, and 1. Okay, I can't also determine the electron spin because I don't know the electrons here. All right, and then we're going to go to the third energy level. N is equal to 2. For the third energy level, L is first going to be 0. Yes, please.
So kindly come again on the ML.
All right.
Why you've written everything stuff.
All right, you are going to take it from here. You are going to understand it here. So if we have got, I've written again a 2, so this is supposed to be a 3. If we have got n being equal to 3, that means L is first going to be equal to, remember L is a number which is equal to 0 up to n minus 1. Okay, so that means the first number always is going to be 0. Now if we say n minus 1, of course we know that is going to, here we've got n being equal to 3, so L is going to be 3 minus 1, which is 2. So meaning that the first L is going to be 0, the next one is going to be 1, then the next one is going to be what? Is going to be 2. So we're going to have 0, 1, and 2. Okay, because L is always from 0 up to n minus 1. Okay, meaning that ML, remember ML is between negative L and positive L. When L is 0, we don't have a number between this, so that means ML is just going to be 0. So if we come to 1, ML is going to be between negative and positive 1, meaning we're going to have negative 1, 0, and 1. And then for L is equal to 2, meaning ML is going to be between negative and positive 2. So that will be negative 2, negative 1, 0, 1, and 2. Okay, we don't also know the electron spin. The electron spin will be determined by the electrons. Are we okay? Are we okay? Or let me say, any question? Yes, please go on. Yes?
I'm saying yes. Yes, everything is okay.
Alright. Now, from what we are able to see here, this ML is what determines, remember we said the the N is representing what? The N represents the shell, L represents the subshell, L represents the orbital. This should tell you that, even for biology, this information is important. This should tell you that in the first energy level, you only have one orbital, right? In the second energy level, you have got one, two, three, four orbitals. In the third energy level, we've got one, two, three, four, five, six, seven, eight, nine. So this tells you that you have got how many? You've got nine orbitals in the what? In the third energy level. Now, you need to know each orbital can only have a maximum of 2 electrons. Each orbital can only have a maximum of 2 electrons. That's why the first energy level can only have 2 electrons maximum in its shell. And then the second energy level, since it has got 4 orbitals, it can have a maximum of 8 electrons. The third energy level, since it has got 9 orbitals times 2, it can have a maximum of 18 electrons. Alright, so you need to know how many electrons are found in each orbital. Am I clear here? Are we good, or there's someone who is left out somewhere? Alright, so the quietness tells me that we are fine. If not, now that we have understood this, we also need to know that an orbital looks like this. Okay, an orbital looks like this, meaning that uh, an electron can either point up or point down. That is what we are calling the electron spin. So depending on the electrons that are in that orbital. Okay, so when you are giving the electron spin in an orbital, you are going to give the electron spin of the last electron. So in this case, the last electron here is going to have ms, which is negative 1 over 2. This one has got an electron spin of positive 1 over 2. Okay, so please, we need to know this. All right, we need to know this. So we talked of orbitals. We have talked of orbitals, and remember we have said the angular momentum quantum number describes the shape of the what? The shape of the orbital. So we should be able to know. All right. Now again, one thing that I've not told you is this. Whenever, take note of this. L, which is angular momentum quantum number, describes the shape of the orbital. Whenever you have got L being equal to 0, you should know this is an s orbital. Whenever you have got L being equal to 1, this is a p orbital. Whenever I've got L being equal to 2, this is called a d orbital. Whenever I've got L being equal to 3, this is called the F orbital. L is equal to 4, this is the G orbital, the SPDFG. So this is where what we are going to understand SPDFG configuration comes from. Okay, am I clear with this? Okay, so what? Okay, so please you need to know every time L is equal to 0, that is an S orbital. L is equal to 1 is a P orbital. Okay, L is equal to 2, that's a D orbital. So whenever you are representing an electron, you should represent it with all the four quantum numbers. Then you have described it fully. Okay, now before understanding that, we need to understand, since we have said the angular momentum quantum number L represents the shape of the orbital, right? It represents the shape of the orbital. And we've said when L is equal to 0, this is an S orbital. When L is equal to 1, this is a p orbital. When L is equal to 3, this is a d orbital. I've gone to 3 before 2. Okay, this is d, spd. When L is equal to 3, this is a spdfg. All right. Now, now the structures that you just need to understand are the first two. The last two you don't need to know how they look. All right. So for the s orbital, it looks like it's oval. Okay, more like a circle. That's how it looks. That's the s orbital. And then for the p orbital, remember when L is equal to 1, ml, you can have what? Negative 1, you can have 0, you can have positive 1. All right. So for the p, you are going to have three types of orbitals. So you can either have px, you can have py, you can have pz. So it just looks like infinity. That's the symbol for p. Okay, that's how it gets to look. That's how it looks like, the p orbital. So you need to understand, at least you need to know how to draw the p orbital and the s orbital. Okay, apart from this, there are some other orbitals which would be, which I've seen in exam questions, they're asking for a person to draw. Okay, so actually these orbitals I've put here, we can write a Cartesian plane, a xy plane, like this. I'm going to put this, I'm going to put this, I'm also going to have this. So let me say this is the z-axis, this is the x-axis, this is the y-axis. You need to label them if they ask you to draw. So I've got 2px, which is going to, first I've labeled this as y, so I need to draw it along the y. So it's just a symbol like that. That is 2, this is py. And then we are going to have px, which goes like that. And then pz is going to go along the z-axis like that. So these are the orbitals. Now there are some other orbitals that you should be able to know, which I've also seen in some questions. They just ask, draw this orbital. Now those are not, of course they are not even going to be described by these quantum numbers that are here, but you just need to know them for that case. So we have got what we call a dxz orbital, we have got a dyz orbital, we have got a dxy orbital, and you also need to know, let me start by writing this at the end, dxz, you have got dyz, you have dxy, and then you have got dx squared minus y squared. Okay, those numbers you're able to see are down, and then the last one you have got dz squared. So at least we should be able to know these which are here. Okay, now how do you draw the dxz? So this one you can see you have got x and z, you don't have y here. That means this one will more like the y-axis is going to pass through this orbital. So what we're going to see is something like this. I'm going to put Okay, I'm going to put it like this. I can actually just write here. I'll be changing them. Okay, now when you're writing the Cartesian plane, actually you swap them. This one, which is the y-axis, it becomes z. You flip it, and then which is the x? This is the x-axis. This is the y-axis. But some people would write still y here, z still there. All right, so that doesn't make things wrong. So if you are talking about this orbital, the dxy, just to avoid confusion, let me just write it the same way you know it. I'm going to put x here. I'm going to make this as the z. I'm going to make this as the y. But just know that it is flipped. So the y becomes the z and the z becomes the x. The y. Alright. So for the orbital dxy, I'm saying you can't see a y here. So what this orbital is going to look like is it will look more like it is the y is passing through it. Okay. So what you are going to see is something like, how am I going to put this? For me to put it properly, let me just swap these. I'm going to put z here and then x here and then y here, so that you can just, for the sake of seeing, it's going to pass more like this. Okay, and then it goes like this, and then it is like this, and then it's like this. So it's more like you have got a butterfly, and then there is a line that passes on the middle, like it passes on the middle like this. It goes the other side. Now you can't see how it's passing, so it is going the other side, is passing on the middle. So that same one which is not here, that is not mentioned here, is this same line that you can't see. Okay, so that means if it is dxy, this line, that if it is dxz, this line is going to be y. Okay, and then if it is dyz, that means that this line that you can see is going to be x, that is passing. And then if it is dxy, you can't see what? You can't see a z there, that means this line is going to be z. Right, so that is this orbital. That is how it gets to look like. Now for the dx squared y squared, I think this one can be even interesting. If I draw this one like this, I put this one like this, and then I'm going to put another one going up. Maybe this one is going to be even more clearer, and then we are going to have orbitals like this. Okay, we have got this one like this. We also have another one like that. I hope it is a little bit clear. So this one, you've seen that, like this one which is going up. Okay, this one which is going up is more like passing through the center, and then it goes up like that. So obviously, if you are talking about dyz, this means that this axis, okay, supposed to be what? If we are talking about dyz, supposed to be x, because it's the one which is not here. That's the one which is supposed to cut this like on top. So that is what you need to know about the dxy, dyz, and dxz. That means that if I'm talking about dxz, if I'm talking about dxz and then drawn it like this means that this line which is passing, going on top like this, is the one that is not here. That is going to be the y. This is going to be the y. But you need to draw them in such a way that each axis is represented well. You know that the x-axis is supposed to lie like this, and then the y-axis is supposed to lie like that, and then you have got the z-axis which goes up like that. We can change the drawing depending. Okay, so if I want something to more like pass, to be dx, I mean dyz, that means it should be more, the x-axis should be more like the one which is cutting it like that. So I need to draw a symbol, something like this, and then it's going to more like pass like that. I don't know, just best I can draw it, but something like that, if you are able to see. Okay, there was a question. Do you have a question?
Yes, so we had a question actually. I didn't understand that the diagram that you wrapped. But since you wrapped it, it's okay.
All
I
right.
won't understand.
Okay, so now we have got the dx squared y squared. For this one, the two which are mentioned is where the graph is going to more like cut. The two which you are able to see here, you have got the x and the y. Okay, so dx squared y squared is going to pass along this which you are able to see. So it goes like this, and then it also passes like this. So that means the y-axis, it doesn't, the z-axis, it doesn't pass there. Okay, that is dx squared y squared. It passes more like on those same axes which have been mentioned. Now the other orbital which is trick is dz squared. So for dz squared, this one is going to be the z-axis. We're going to make this as the y-axis. This is as the x-axis. So for this one, z squared, it goes along the y. Like it will go something like this, and also like this, and then you are going to have like something like lines like that. So that's how this orbital is drawn. Okay.